Hello everyone, welcome to Marketing Research MKTG 457. This is chapter 13. Okay. In chapter 13, let's talk about the big data basics, describing samples and populations, how to describe samples and populations, and some basics about big data. Okay. After studying this chapter, you should be able to know the basic descriptive statistics to analyze data and make basic inferences about population metrics. Okay? And you're going to use these methods, in your group project. Okay? You should be able to distinguish among the concepts of population, sample, and sampling distributions. Okay? Explain the central limit theorem, and use confidence intervals to express inferences about the population estimates. When you estimate something about the population, you can use confidence intervals to do that. Okay? And the major issues in specifying sample size and how to assess the potential for non-response bias, etc. Okay. Now, all the statistics in this chapter are univariate in the sense that only one variable is involved. Univariate, okay, not bivariate or multivariate. It's univariate, meaning there's only one variable involved. Okay. We're going to provide a good background for understanding equations related to some sample size requirements. Okay. These equations complement the material in the previous chapter. Okay. It provides us with a better understanding of the usefulness of a particular sample. Okay. Descriptive statistics and basic inferences. We start with the raw data. What is raw data? Raw data are simply numbers and words with a little meaning. Okay? They're raw, okay? It's not refined. The most basic statistical tools for summarizing information from data include the frequency distributions. You can count the frequency distributions, proportions, measures of a central tendency and dispersion, and the metrics provide means of comparison. You compare two groups of data. Okay? The combination of summary metrics from basic statistics and the valid sample proves vital in making effective marketing and business decisions. Okay? Summary metrics from basic stats and the sample, a valid sample, provides proves vital in helping make business decisions. Okay? Inferential statistics allow inferences about the whole population from a sample. Okay? You can get data from a sample, and you can inference that about the population. Okay? And there are two applications of statistics here: to describe the characteristic of the population or sample, and to generalize from a sample to a population. Okay? Describe and generalization. Description and generalization. Okay? Why are sample statistics and population parameters? What are sample statistics and the population parameters? Okay? The primary purpose of inferential statistics is to make a judgment about the population. You want to study the population, okay? Entire population. Okay? And sample is just a subset or a relatively small fraction of the total number of elements in the population. For practical reasons, it's not possible to survey the entire population, right? And only the U.S. government, Uncle Sam, is doing that with the census of everyone. And for businesses, or nonprofit groups, you want to study only a small sample. But the small sample, as we said earlier, could provide good information about the population as well. Okay. Sample statistics are measures computed from sample data. We call this something you computed, calculated from sample data is called the sample statistics. Okay. Population parameters are measured characteristic of a specific population. Population parameters of a specific population, right? We normally use Greek lowercase letters to denote population parameters. For example, mu, or that's for the mean, or sigma, sigma for standard deviation. We use English letters to denote sample statistics. For example, X is for the mean of sample, S is for standard deviation. So every time you see a mu or a sigma, you know it's about population, right? Every time you see X or S, you know it's for sample, okay? We're going to use that convention, okay? Frequency distributions. We can construct a frequency table or frequency distribution as one of the most common means of summarizing a set of data. Okay, we have a huge set of data, maybe collecting, tens of thousands, even hundreds of thousands of observations, right? And it's not that convenient to show that, as the entire data set. You want to use frequency tables or frequency distribution as a way to summarize a set of data. Right? Now, what is the frequency? Frequency of a variable is the number of times a particular value of variable occurs. Okay? It's the number of times it occurs, how frequent it occurs. Okay? It's frequency. The distribution of relative frequency. Distribution of relative frequency, or a percentage distribution, is divided by dividing the frequency of each value by the total number of observations and multiply the model result by 100. It's percentage distribution, percentage, if you know how to calculate that. And the probability is a long-run relative frequency with which an event will occur. Okay, it's a likelihood. Long-run relative frequency. It's the likelihood that something is going to happen. It's a probability. Okay? Give you some example here. Right. This is a frequency distribution of a deposit, bank deposit. Okay? And the deposit amount, you take money to the bank to deposit. The deposit could be under $3,000, 3,000 to almost 500, 5,000, 5 to almost 10, 10,000 to almost 15, or 15,000 more. Right? If you count the number of people making those deposits in the bank, you look at the frequency. That's the number of people who hold deposits in each range, right? Or each range. Okay? Under $3,000. Okay? Now this actually should be the deposit, the total amount of deposit, not each time a deposit is made. It's the total what you have in the savings account or checking account, the total deposit. Okay? There are 499 people who have their deposit account with under $3,000 in the balance. Okay? 530 people with 3,000 to 5,000 between that. 5,000 to 10,000, 562 over between that, 718, 15,000 or more, 811. Right? And if we add all these up, there's 3,000 people, 3,000 customers of the bank. The distribution of the frequency distribution of deposits, by these categories is this. Okay, 499, 530, 562, 718, and 811. Okay, that's frequency distribution. Okay, but the frequency distribution is not that convenient to use, and also is not hard to compare with another bank. Right? Sometimes we use a percentage distribution deposit. So how do we calculate that? Okay, if we have, let's say, first one, right? And if you divide the number of the deposit accounts by the total, we get a 16%, 16%, or 0.16, right? And 17% are in this range, 18 this range, 23 this range, and 26 here, right? You add them together, it has to be 100 because that's the total all your accounts. Okay, so you use the number of deposits or accounts in that each category, right, and divide by the total, 2,000, 3,000 some accounts, right? You get a percentage. Okay? This is a percentage distribution of deposits. Okay? So then proportions. What's the proportion? Okay? A proportion indicates the percentage of population elements that successively meet some standard on the particular characteristic. Okay? The characteristic could be, say, like have a bank deposit amount between 5,000 and 10,000, okay, for example. Okay? It may be expressed as the percentage, a fraction, or decimal number. Okay? Percentage, for example, 20%. How do you describe 20%? Okay? You can see it is a 20 out of 100, or 1 out of 5. Right? That's also 20%, or a decimal number, 0.20. Okay? They all mean the same thing. Okay? So make sure you know how to switch between percentage, fraction, or decimal number. A percentage of 20% is same as a fraction of 1 over 5, 1/5, or a decimal number of 0.2. Okay? Here example here of probability. Right? Probability distribution is just the frequency expressed as a as decimal place, decimal number. Okay, and as more up, you should get 1.0. That's the total probability, and all the probability together. So what the probability distribution table is showing us is that there's a chance, there's a 0.16 chance or 16% chance somebody is in the deposit account is under $3,000. Okay? There's a 17% chance the deposit account is under 3,000, between 3,000 and 5,000, etc. Okay? That's using probability distribution to describe the deposit accounts. Okay? Top box and bottom box scores. In business, they use top box score versus bottom box scores. A top box score generally refers to the portion of respondents who choose the most favorable response towards the company. The portion that would highly recommend the business to others, or the portion expressing the highest likelihood of doing business again. Right? We call that a top box score. Right? Top box score. Right? And the logic is that the respondents who choose the most extreme responses are really quite unique compared to the others. Yeah? That's the idea here. Okay? Managers should examine the bottom box score, right, score, the portion of respondents who choose the least favorable response to some questions about the customer opinion. Okay? That's where you need to pay attention to. You want to change their attitude, change their opinion about your product or company. Okay? And that's the more diagnostic of customer problem. Okay, it often signals a need for some managerial reactions. You need to do something. Do something to change the situation. Okay. Now let's talk about the central tendency metrics. The mean, the most important, the simplest, most common one. The mean is arithmetic mean, average. Okay, is a common measure of central tendency. The sum of all the observations divided by the number of observations. The sum of all the observations divided by the number of observations. When I give your test results back, I normally give you the mean. That means that you say I have 35 students, 35, 40 students in my class, this class, right? And add all your scores on the test, right? All 40, 35 of you, right? Add them up and divide by 35. That's the average, arithmetic average, right? It's a major central tendency, shows, how the overall class is doing. The average is so and so, okay? Okay, that's how it is calculated, right? We use sample mean, the sample will be, you remember sample, we use English letter. For population, we use Greek letter, right? A sample mean X bar, X with a bar on top, we read it as X bar, can be calculated when there is not enough data to calculate the population mean, which is the mu. And we don't have that population, we can calculate the sample. Okay? And the sample could be or should be a good indicator if do things right. It can sometimes be misleading, particularly when extreme and on values or outliers are present. Like for example, let's say you have let's calculate our personal income, for example, income per person, right? We have 35 students here, including me, right? Everyone has an income. Let's say you will have an income upon your graduation, right? And we average our income together. Average our income, we come up with a number. The average individual income in America nowadays, I think, is around $40,000. $45,000. The average household income in the country is about $50,000, $55,000, $60,000. Okay, let's assume that Elon Musk, Elon Musk is among us, right? And his income, I don't know how much he makes, hundreds of millions, dollars. He makes a lot of money, right? And he was, the world's most the richest man, and now I think he's second now. But maybe when more companies are offered for trading, go public, I think his wealth will go up again. But anyway, if we include his number, his income, in calculation of our income, all of us, including him, the number is going to be huge, right? We don't know how much. It's probably likely going to be hundreds of thousands of dollars or millions of dollars, But that's obviously not very indicative of the majority of us, okay? And he's an outlier. It's an extreme number, okay? So that's why the mean, if you just calculate mean, it could be misleading if you have an outlier or extreme numbers values, present. Okay? And what do we do with that? We have other ways to describe. Okay? This example of calculating the number of sales calls per day by a salesperson. You can see the salesperson, you get 1 through 8 of them. Names are Mike, Patty, Billy, Bob, John, Frank, Chuck, and Samantha. Right? We can call this, name them as variables. X1, X2, X3 through X8. Okay? The number of calls they make per person, by the person on the day, per day. Mike made 3, Patty 3, made 4, Patty 3, Billy only 2, and 5, 6, 3, etc. Right? And how do you calculate the average number of calls? Okay, you add them up. That's 26, right? And what you do, you divide by the total number of people here. That's 8. Okay? Okay, to get your average number. Okay. Next measurement of central tendency is the median. The median. Median is what? Is the midpoint of the distribution, or 50th percentile. We used to use 100 percentile, right? 100 percentile, 1% through 100%. Okay? We can also use 50th. We can in 100%. 100%, the 50 percentile is what? Of the 100, 50 percentile is what? in one in the middle, right? So the value below which half the values in the sample fall, that's the midpoint. That's the midpoint. In other words, if we have, say, 35 of us, 36 of us, including me, we rank order our salaries, income from low to high or to high to low. Okay, we count there are 36 of us, 18 of us, 18 and 18, and the one with the middle two, we can average them. You have the 35 view, we can calculate, find the middle one in the middle. Okay, that'll be 17 each, right? 17 each, and plus the one in the middle. So that way we know, we call that number the median. That's a median, right? You can see, do you see the advantage of using median? If you still have Bill Gates in the class, right? And it's not going to change much because he's on the extreme high side, not Bill Gates or Elon Musk, right? And then the one in the middle, it's not affected that much, okay? So it's a better measure of central tendency in the presence of extreme values or outliers. Okay? Yet another matrix for central tendency is called the mode, which is a measure of central tendency that merely identifies the value that occurs most often, okay? And it's determined by listing each possible value and noting the number of times each value occurs, the most frequent occurring one. Okay, it's used for data that is a less than interval with one large peak. One large peak. Okay. Dispersion matrix. And then we want to see how the data, how the numbers are dispersed, right? How widely distributed it is. Okay? So dispersion matrix is accurate analysis of data, also requires knowing the tendency of observations to depart from the central tendency, okay? Away from central tendency. That's called dispersion, right? There's another way to summarize data is to calculate the dispersion of data, or how the observation vary from the mean. Okay, vary from the mean. Okay. So example of sales levels for two products with identical average sales. Okay, if you look at two products, product A, unit product A, and product B. Okay, look at the number of the month of the year where this number of the either A or B are sold. What do you see here? You see in unit for product A, from January through December, it's 196, 198, 99, 200, 200, and then 202, right? You see, there's not much variation, right? It's not much variation, it's always around 200, and the average is exactly 200. Right? But if you look at product B, though, which one is the highest number you can see? 261. December 261. What the lowest you can find is probably 150, right? You can see from 150 to 261 is a huge variation of the sales, And then if you average them, it turned out to be 202, exactly 200, right? So it seems to be that if you just use the average or mean to look at the sales of the two products, they don't have there's no difference, the whole 200, right? But if you use a dispersion to tell, you can see which one is more diverse, more dispersed, or more variance, more variations. It's product B, right? From lows of 150 to highs of 261, versus unit A, the lowest is only what, 196 to 202. There's not much variation. It's very consistent. Okay? You can see if you put on the chart, you can see this is the value on the variables 170 to 230. Okay, you can see this is the frequency, and this one you can see between 185 to 215. It has less variation, and mostly in the center around 200. We can say that it has a low dispersion. The other one from 173 to 230 has a much wider distribution. We can say it has a higher higher dispersion. Okay? Range. Range is another one. And to talk about the dispersion. The simple measure of dispersion is distance between the smallest and the largest value of frequency distribution. Normally the largest minus the smallest. You have the range. Okay. It does not take into account all of the observations, right? It just involves the largest and smallest, right? It indicates extreme values of the distributions, right? And in a skinny distribution, values are short distance from the mean. In a fat distribution, the values are spread out. You can see. Right? Excuse me. The interquartile range encompasses the middle 50% of the population. That is between the bottom quartile and the top quartile. Okay, we can use a percentage. We can also use percentile, right? We can also use quartile. Percentile, we divide the whole thing into 100%, right? 100 portions. Calculate percentile, right? You can use decile to divide the thing into 10. Look at the decile. We can use quartile. A quartile just divide the whole thing into 4 quarters, right? First 25, second 25, third 25, and bottom 25. The middle 200, the middle 50%, that's interquartile. Called interquartile, okay? That's range. Then let's talk about deviations, right? Deviation scores. Deviation score is a method of calculating how far any observation is from the mean. Is to calculate the individual deviation scores, how far each one is from the mean. Okay, a deviation of any observation from the mean can be calculated by subtracting the mean from that observation. If you subtract the mean from that, you get a deviation. Okay. Obviously, you can have a minus deviation or a positive deviation. Okay. Then there's a term called standard deviation. Standard deviation. This is, you can see, is one of the most important, most critical, most widely used measures in statistics. Very important, and is often is a very significant one to use in many applications in stats. Okay? It is perhaps the most valuable index of spread or dispersion. Most valuable index of spread or dispersion. Other measures of dispersion that may be used, like average deviation. You can average deviation determined by calculating the deviation score of each observation and summing these scores, then divided by the sample size, and that's average deviation. You can calculate by the variance. Variance is used for describing the sample variability. Will equal to 0 if only and each and every observation in the distribution is the same as the mean. Okay, that's variance. Okay. Why do we want to use standard deviation? Okay, what's standard deviation? That's the square root of the variance for distribution. It's called the standard deviation. The square root of variance. We use S, the symbol for the sample, standard deviation. Okay, this is how it's calculated. Does it look complicated? It's actually not. It's not complicated at all. Not complicated at all. Okay. As I said, standard deviation is square root of variance, and this S squared is the variance. So S squared, and you take the square root of that. That's S, right? That's your standard deviation. And how is this standard deviation calculated? Here is a big square root number, the square root sign. You can see that we find the square root of this number in the middle. And what's in the middle here? What's inside of that here? Is xi minus x bar squared and summed and divided by n minus 1. What is xi? Xi is each and every observation in the series in the data. Let's say calculate Again, let's see how we calculate our income, standard deviation of our income. Let's say 35 of us, 35 you plus me, 36 of us, right? And each one of us, our income, how much you make or how much you guys will be making, right, is xi. And previously we calculated our x bar, which with x bar, sample mean, right? All 36 of us, our salary or income, that together divided by 36 is our average salary, average income. So that's x bar. It's the same for the entire class. And you have to use the first person's salary minus the mean, average, and square it. The number xi minus x bar could be positive or negative, right? But if you square it, it's will be positive, right? So we do that for the first person, find the difference, squared. And the second person, squared, and find the difference and squared. Third person, difference squared. Fourth, difference squared. And including me, we got all six of us, the difference from the mean squared, and then big sigma here means we add them all up together and divided by n minus 1. Excuse me. N in this case 36 minus 1, 35. Okay, we find that the division here, and then we take the square root of that. That's our standard deviation. That's how it's calculated. Okay, here I give you an example of standard deviation of number of cells called per day for 8 salespeople. Okay, we know the average we calculated before is 3.25 calls. Okay, we have 8 salespeople here, right? So the first person makes four calls minus 3.25, the average, you got a 0.75. 0.75 squared is 0.5625. And the second person made phone calls less than the average, right? So 3 minus 3.25 give you minus 0.25, right? And that squared also become a positive number, is 0.06. It's the same for all 8 people, right? We add them all up, all these up, you get 13.5. 13.5 is here, okay? 13.5. N in this case is 8, 8 minus 1 is 7, 13.5 over 7 is 1.9286, okay? Just less than 2. You take a square root of that is 1.3887. Excuse me. That is the standard deviation of this set of data, this series of data. Okay? Distinguishing between population sample and sample distribution. Okay? Let's talk about normal distribution. A normal distribution. Yeah, that's one of the most common probability distribution in statistics. Normal distribution. Okay, it's also known as the normal curve. You heard about the word bell curve, right? Bell curve, normal curve. That's what it's about. Okay, it's a bell-shaped, beautifully, symmetrical, bell-shaped normal curve. Almost 99%. 99% of its values are within 3 standard deviations from the mean. We'll get to that number later. Okay, because basically this is normal distribution. It started out from people's measurement of a person's IQ score. If you haven't taken the IQ test, you probably should try that. If you score like 120 or above, you're very smart. Okay, 140 or above, you're genius. Okay, around 100, not bad. You're around the average. Okay, under 85, you're below average. 70, 55 is below average. That's okay. It's just one way of measure your people's IQ. But you can argue it may not be the best way or the only way to test people's IQ. But that's just one measurement. But this measurement, interestingly, it follows this bell-shaped curve. we call it normal distribution. What do we mean by that? Okay, the standard deviation of IQ test is 15. Okay, so as I said, the IQ test is designed in a way that the average IQ score is 100. So if you score 100, congratulations, you belong to the most frequent group of people. Your IQ is about same as the majority of group of people, right? That's 100. You can see there's the highest point here in the curve. The study also found that 34% of people have the IQ score between 85 and 100. Well, another 34% have the score between 100 and 15. So 15 is standard deviation. So 15% above or below standard deviation. Okay, there's one standard deviation above and below. Okay, you have 34 plus 34, you have 68%. So 68% of people will have their IQ score within one standard deviation from the mean of 100. You see what I'm saying? So 68% of our population, people on Earth, will have the IQ score between 85 and 115. 68%. Okay? And if you add this two standard deviations out, 100 minus 15, you get 85, minus another 15, you get 70 on this side, right? On the other side, you add 15, 115 plus another 15, you get 130, right? Two standard deviation on both sides of the mean, right? How many people do you have? It's about 95% people. 95% of people are within the two standard deviation, or have having IQ score between 70 and 130. Okay, 130. And if you take three standard deviations out, okay, the 55 to the other side will be 130, 145. I don't see here, right? And you know how many people in that category? It's 99.7%. 99.7%. That's why I said if you have IQ score over 145, you're a genius. You belong to the 0.02% of people, or maybe 0.01 because you're one on each side, right? So it's yeah, very smart. Very few people achieve that. Okay? That's the IQ score or normal distribution. Okay? Normally, we use the standardized normal distribution. Standardized normal distribution is a specific normal curve with several characteristics. Okay, several characteristics. Yeah, you can see for most of measurement of most things in the world today, you may have a curve normal distribution, but the bell curve could be skinny and tall, or could be fat and low, and wide and fat and low. Okay, so in order to conveniently use tables to show the percentage or probability, people come up with the standardized distribution. We standardize the normal distribution, making it into what we call the standardized one. Standardized distribution has certain properties or characteristics. It's symmetrical about its mean. Okay? The mean identify its high point or the mode, and the vertical line above which is the curve. This curve is symmetrical, okay, around the line. Okay? And the normal curve has an infinite number of cases. It's continuous distribution, and area under the curve has probability density equal to 1.0 because it covers all the possibilities. Okay? The standard normal distribution has a mean of 0, okay, with 0 mean, and has a standard deviation of 1. Okay? The standard distribution is like this one here. You see, this is the standardized normal distribution. Okay, the mu is the average is 0, the mean is 0, standard deviation is 1. This is -1, -2, -3, right? And +1, +2, +3. Okay? That's standardized normal distribution. Okay. Standardized normal distribution and Z-scores. How do you come up with the standard distribution? How do you standardize it? The standardized normal distribution is extremely valuable because we can translate or transform any normal variables x into the standardized variable. We got z, right? From x, any normal variable, and we can translate that, transform that into standardized normal, and we call it z-score. Z-score. Okay, how do you calculate z-score? The z-score I'll show you just a second. Z-score has many pragmatic implications for the marketing researcher. A typical standardized normal table allows us to evaluate the probability of the occurrence of certain events without any difficulty. Make it easy to use tables, standardized tables. Okay, this is how Z-score is calculated. Okay, how it's calculated: Z-score equals X is your sample mean, and mu is the population mean, and divided by your standard deviation. If you do this transformation, your normal distribution will become a standardized normal distribution. And X will be transformed into Z-score. Okay? You subtract the mean from the value to be transformed and divided by the standard deviation, all expressed in original units. Okay? In the formula, note that the sigma, the population standard deviation, is used for the calculation. Okay? Where mu is a hypothesized or expected value of the mean. Okay? Of population. Example of that, standardized values. Let's suppose that the toy manufacturer has experienced a mean sales mu of 9,000 units and the standard deviation of sigma of 500 units during the month of September. Right? A toy manufacturer have mean sales of 9,000 units a month, is a month in September, and 500 units. Right? The production manager wished to know if the wholesaler would demand between 7,500 and 9,625 units during the month of September this year. Now, how do you do that? Between 75 and 9,600, you can use this score. Because there are no table in the back of a textbook showing the distribution of a mean of 9,000 and 7,500, we must transform the distribution into standardized normal with that simple formula, the Z-score. Okay, we're going to convert that 7,500 minus the mean of 9,000 divided by 500 equals Z-score minus 3. And the other end 9,625 minus mean 9,000 divided by 500 standard deviation give you 1.25. So basically, we want to find out the probability between minus 3 and 1.25. Okay, so when Z is 3, the area under the curve, the probability is 0.499. When Z is 1.25, the area under the curve is 0.394. Okay, so the total area under the curve is 0.499 plus 0.394 give you 0.893. So the chance that the wholesaler would demand between 7,500 and 9,625 units is 0.993, or 89% of chance. Okay, the area under the curve portraying this computation is shaded area in this one here. Okay, so therefore the sales manager knows there's a high probability the sales will be between that numbers. Okay. Okay. These are the Z-scores, standardized normal table, and their area under half of the normal curve. Okay, this is the standard deviation from the means. Okay, here standard deviation from the means, in units, tens of units. Okay, this is the score. Okay, and this is a table you can use. Okay. Here shows that. Okay. This is the shaded area of a z-score 0.394, right here, 394. And this green is a shaded area between -3 and 0, okay, and 3 and 0. So this is the between the 7,500 and the 9,000 mean, and this one is over 9,600 and 0. And so this is how this probability is calculated. We add these two areas together, okay, that's the total possibility that someone, the wholesaler, will order the units between here and here, okay. Standard value can be computed from flat or peaked distribution, resulting in a standardized normal curve. As I said, the normal distribution could be like this one here is a flat, okay, and it could be a skinny one like this one here, tall and skinny, okay. If you do your Z transformation, standardize it, it's going to all be like this in the middle. That's a standard normal distribution, the perfect bell curve with a mean of 0 and standard deviation of 1. Okay. Okay. Let's talk about population distribution and sample distribution. Okay, now what's a population distribution? That's a frequency distribution of the population elements. That's population distribution. Okay. The mean and standard deviation represented by the Greek letters mu and sigma. Mu is for the mean, sigma is for the standard deviation. Okay. Sample distribution is a frequency distribution of a sample. It's called what do we use again? English letters, right? The sample mean is designated with an x bar, and a sample standard deviation is s. Okay. There's a theorem called the central limit theorem, which is very important, very critical, very useful for our practical use. Okay. What does the theorem say? Okay. Basically, the theorem says that as the sample size n, the sample size of sample, right, increases, we increase sample size from 200 to 500 to 2,000, 5,000, or even 100,000, right? The distribution of the mean, every time the sample size increase, there's a new mean, right? New mean x bar of the sample. Every time you increase the sample size, you have more to calculate. Then you have a new number for the mean x bar, right? But as n increases from small to great, right? The distribution of the x bar, which is a random sample, right? Random sample, depending on how many sample you have, right? The x bar, the distribution of that actually, approaches a normal distribution. Interesting, huh? Yeah, that's what the theorem is about, right? As n increases, the distribution of the mean x bar approaches and become a normal distribution for the new distribution. And this normal distribution will have a mean of mu, as population mean, and the standard deviation of sigma divided by the square root of n. That's what the theorem is about. Okay? So the central limit theorem works regardless of the shape of the original population distribution. It doesn't matter the shape, right? The theoretical knowledge about distribution can help solve practical research problems. Okay? And it's eliminating parameters and help determine the sample size. Okay? This one shows that the mean distribution of any distribution approaches normal as n increases. Yeah, this is here. This is the n of 60. Okay, this is n of 5. You can see that. Okay, right. Okay. And this is n of 60. You can see the distribution of mean is approximating that of normal curve. The more you have, the better. The more likely it's going to be like a bell curve. Okay, that's what the theorem is saying. Okay, This is an example of population distribution hypothetical toy expenditures. This is if you look at the children, Alex, Becky, Noah, Tobin, George, Freddie. There's a number of the money they can spend on toys, expenditures. Different number of dollars. Okay. And if you calculate the population mean, you can add them all up. It's $21 divided by 6. You get 3.5. That's the average they spend on toys. Okay? That's an example. Yeah. We can also do estimation of parameters and confidence intervals. Right? When you estimate the population from the sample, you can use the X bar, right? X bar, the mean of sample, to estimate the mu, the population mean, right? But that's just a point estimate, just a 1 point estimate, right? In point estimate, our goal in utilizing statistics is to make an estimate about population parameter here. Okay? The population mean and the standard deviation are constants, but usually unknown. We don't know. Nobody actually measured the entire population, right? So the mean and standard deviation is unknown to us, right? So when we use a point estimate, an estimated population mean is in the form of a single value, which usually is a sample mean. Okay? And instead of doing that, oftentimes we can estimate the population mean with the confidence interval. Instead of a mean, one single point estimate, a single number, we can give a range. Right? One would be extremely lucky if the sample estimate were exactly the same as the population value. So you'll be really lucky to have that. Right? So normally we don't. Therefore, we rather than giving you an estimate of point, one number, we can give you an interval, a little range. A confidence interval estimate is based on the knowledge that the mu equals X bar plus minus a small sampling error, right? We know it is around the mu, is around the average, right? Around edge, but it could be higher, it could be lower. It's normally a small number plus or minus that, and your mu, your population parameter, it should be within that little range or within that interval. Okay? So after calculating an interval estimate, we can determine how probable it is that the population mean will fall within this range of statistical values. Then that'd be nice, right? Instead of saying, hey, the population mean is this much, we can say we are 95% confident that the mean will be within this range. Wouldn't that be nice? Or we can even say 99% confident or 90% confident. You can choose your own confidence level. Okay. So confidence level is a percentage or decimal that indicates the long run probability that the results will be correct. Okay, that's the confidence level. Okay. So traditionally, researchers have utilized a 95% confidence level. Okay. But you can use 99 or 90, whatever. Okay. So what are the steps to step-by-step calculation of confidence interval? First, you calculate the X bar from the sample mean, and then you assume the mu is unknown. You estimate the population standard deviation by finding S. S is again is a sample standard deviation. Okay, sample standard deviation. Right. You estimate the standard error of the mean using the formula. Standard error is S divided by the square root of n. Okay, I see the n increases, as the n increases, the standard error will be smaller. Okay, you understand the standard error. Okay, then you determine the z value associated with the confidence interval desired, and then divide the confidence level by 2. Okay, Then you calculate the confidence interval. When the standard deviation of the population is unknown, a confidence interval is calculated by using the following formula, right? Confidence interval, okay, X bar, that's your F sample mean, plus or minus the Z-score, and the Z value, associated with the confidence level desired, and divided by and multiply the standard sample standard deviation and divided by square root of n. That's your interval. So the X bar plus that number and X bar minus that level will give you the upper limit and lower limit, upper level and lower level, and between that, that's your interval. Okay, that's your interval. Okay. So the researchers also sometimes we need to estimate the sample size for questions involving means. Okay, the researcher must follow these steps, the 3 steps in calculating estimating the size of sample. Okay, first you need to estimate the standard deviation of the population. You make a judgment about the desired magnitude of error, and then determine a confidence level.